My name is Rob Alexander. I'm a Seattle-based solutions architect, and today we're going to dive into EBS, Elastic Block Store, specifically covering some of the new things we announced today, getting into a lot of the best practices around performance, security, management, and let's get into it. So I'd like to start with a little background on the evolution of EBS as a service. Why did we build this service? Back in 2006, 10 years ago, EC2 launched. And EC2 in the beginning, the only storage available to it was local instance store. So hard disks that happened to be attached to the physical host that was hosting your instance, that was the only option. And that was fun. And customers obviously had a few more requirements beyond that. When the instances would go away, their data went away too, which was obviously not ideal. So we started hearing from customers and feedback that we'd like something a little bit more persistent that we can rely on beyond the actual instance itself. So EBS launched in 2008. With our first volume type, we only started with one, and that was EBS Magnetic. So it was a hard disk drive-based platform, which did exactly that, persistent disk store, and allowed customers now to save their data isolated from the actual instance and be able to flexibly move that data around between their various instances. But then we started to get more feedback, and customers said, okay, that's great, we've got persistent data now, but we'd also like some consistency in the level of performance. And also, could you maybe build that on SSDs this time? So in 2012, we launched Provision IOPS, which was our first SSD-based platform, and provided low latency and particularly the ability to dial in exactly the amount of performance that you wanted. So you could tell us the IOPS, and with 3 nines of guarantee, we would deliver those IOPS in a consistent fashion. So we're starting to build up on the flexibility and the options of EBS, and customers started asking for, yeah, we really love these SSDs, we love the latency, we love the random I/O performance, but we've got workloads that are kind of variable. We can't really tell you exactly how much IOPS we want from a day-to-day basis. And so we'd like something a little bit easier to manage and not have to actually dial that in all the time. So in 2014, we launched general purpose 2 volumes, also SSD-based. But in this case, the bigger the volume, the more performance. There was a fixed ratio, and all you had to do was tell us how much storage you want, and you got a certain amount of performance based out of that. And then along the way, we've released lots of features to build on all these different volume types, including encryption for both your data and your boot volumes. And also last year, we launched larger and faster volumes. So previously, the largest volume size was a terabyte. With larger and faster, it can now go up to 16 terabytes. And the throughput on those volumes also doubled, so significant performance improvements. So you can see through the years, the evolution of the platform, now you can see a lot of flexibility in the offering of EBS. And now today, with the launch of the new Throughput optimized volume types, the new ST1 and SC1 volumes, we've got a real wide range of flexible options to suit your specific workload. So exactly what is EBS? We talk about it with volumes and volume types, but what is it at its heart? When you launch an EBS volume, what does that mean? It's a container of block storage that is configurable by you as far as how much block storage is in there, and also has performance characteristics that you define according to the volume types that we'll get into those specifically later. And then it's attached to an EC2 instance. Now that attachment happens over the network. So this is a network-based block storage service. You can attach multiple volumes to a single instance, but a volume itself can only be attached to one instance at a time. So you can see here you can separate out your volume types between boot volumes and data volumes. So you start to see you have real flexibility not only in the way you define your storage, so separation of different storage from different storage types, but you have the ability to separate out your storage from your compute and your memory, so that if you needed to scale up your CPU or the amount of RAM dedicated to your instance, you could do that. You could launch a bigger instance, detach and attach the volume, and you're ready to go. Or on the opposite side, if your storage needs were growing, but you actually didn't need to add more compute, so it didn't make sense to you from a cost and performance perspective to launch a bigger instance, you could just grow your actual storage amount. So an EBS volume itself is launched into a single AZ. It's an AZ-specific volume, but it's replicated. All the availability and durability is taking care of you. So every block you write to an EBS volume is synchronously replicated within that same AZ. And that's done beyond the storage you provision. So you only pay for what you provision. You're not actually paying for this synchronous replica of your data. And that leads to some very interesting availability and durability statistics. I mean, EBS is designed to run at 5 nines of availability. The reality is we do much better than that. We get nearer to 6 nines of availability, which, if you consider 6 nines of availability in a single availability zone, it's a very impressive uptime statistic on a per volume basis. And same with durability. So durability, the annualized failure rate of a single EBS volume, is designed to be between 0.1 and 0.2% per year, which is about 20 times higher than your average commodity hard disk drive. So significant value in both the durability of a single volume and the availability of those volumes. Now, beyond that, you also have the capability of taking snapshots or point-in-time copies of your data. So that's a snapshot of the volume that is then copied up into S3. Now, S3, of course, is a regional service. It's not constrained to a specific availability zone. And it also has 11 nines of durability. So now we're talking a much magnitude greater for the preservation of your data. And these snapshots, what exactly are they? How do they actually work? So when you take a snapshot, the first one is a full copy of all the states of the change blocks on your volume. So here you see we have blocks A, B, and C. And it's important to note that when you actually take that snapshot, you're not waiting around for that data to transfer. As soon as that API call for create snapshot completes with a success, it just comes back and said 200 success, you're ready to use that volume again. All the data transfer is actually happening in the background. You don't wait for it in order to use your volume again. And so we move on to the second one. Now, the snapshots are incremental. So as you take more and more snapshots of the same volume, the only thing that's going to be on subsequent snapshots is any change data. So here we see we've modified the C block. It becomes C1. We take that snapshot. So the only thing on that snapshot is the incremental difference. And we move on to the third snapshot of the same volume. We've added 2 new blocks, but we've also deleted B block. And we take that snapshot of the state of that point in time, the state of your data. And now we see we got the 2 new ones and the record that that block has been removed. So what happens if we actually delete these 2? So the system is designed so that the latest snapshot is always the only thing necessary to restore your volume to its state when that snapshot was taken. So even though, for example, the A block is not represented in snapshot number 3, it is actually symbolically linked there. So that if you use that snapshot, then to restore that volume to a new volume, you're going to get the state of that volume at the time the snapshot was taken. So you only ever have to keep that last one. And so the data, when you create a new volume from a snapshot, starts streaming in a lazy load fashion. So here you see A comes in and C comes in. But if, for example, you access this volume and you call the block that hadn't been loaded yet, that block would be loaded to the front of the queue and move in first. So if you happen to hit E and you wanted E, that one would move to the front. It would be populated on your volume itself, and then the lazy load would move on and start loading the rest of the blocks. So you can use snapshots to launch new volumes in other availability zones. You can use snapshots to resize the size of your volume. So if you decide you want you want the same volume but a bigger size, you launch a new snapshot, bigger size, resize your file system to meet that new volume size with the same data as you had before. And obviously, every volume you create has its own replica. You can use snapshots to copy across regions. So this is a very common component of any AWS-based disaster recovery strategy. You can copy them across accounts. You can share them across accounts. And a good representation of this is how public data sets are actually represented. So beyond the snapshots you see where, if you go into the management console, you launch an EC2 instance. If you launch Amazon Linux, if you launch Windows, if you launch any of those are all EBS-backed Amazon machine images. But we also have public data sets, so you can launch data sets ready to go from a snapshot, attach them to your instances, and have full access to data sets like genomic data, census data, global weather, transportation data. So they're all available out there for free. There's a link there if you want to check out the public data sets. So what happens in failure situations? So what if the volume itself fails? So that's a very simple EBS-based client, which is running on the physical host that's hosting your instance, detects that failure, makes the switch to the replica of that volume, and as soon as that switch happens, that volume now becomes the main volume, and it starts replicating its data to a new replica. And this happens in a matter of seconds, and the experience from your instance would be a few moments of blocked I/O. What if you terminate the instance that the EBS volume is attached to? And this is an important piece of housekeeping. I see lots of customers who keep a lot of volumes around because they didn't know about this flag that is attached to every EBS volume. So the delete on termination flag, which if you just create a volume outside of launching an instance, that flag is by default set to false. So if it is set to false and you terminate the instance that volume is attached to, then the volume itself will just endure. It will persist outside of the life of the instance. But if the flag is set to true, which is what it's set to default if it's a boot volume, for example, when you launch an EC2 instance, or if it's any other instance that is attached to the EC2 instance you create when you launch it, those volumes by default will be marked true, and they will be deleted along with the EC2 instance. So make sure that you're keeping good housekeeping with these flags and making sure that you're not taking for granted that when you terminate EC2 instances that the volumes are going with them. You want to make sure that flag is set so you don't have a bunch of volumes sitting around that aren't doing anything and not attached. So what if the instance itself fails? Obviously, if the flag is set, the volume persists, and you can launch a new EC2 instance and attach it to that volume. But there's actually a unique feature enabled by EBS, which is called EC2 auto recovery. And it enables you to automatically, without anything on your behalf, any action to be taken on your behalf, recovers that instance on an instance failure, and that instance comes back on new hardware with all the characteristics that former instance had. So, EC2 over the years has developed this very robust system of health checks that cover both the hardware and software of not only the physical host, but your instance itself. It covers things like power, networking, the applications like the hypervisor running on the physical host. So all these things are all being health checked in the background, and they surface up to you in two ways. So they're all combined, and they have a system level check. These are available in CloudWatch. So there's a metric for a system level check and an instance level check. And until this feature, the EC2 auto recovery, was available, there wasn't much you could do with these checks. They would alarm, they would send you an alarm, but as far as the actions you could take, you were pretty limited. You could just launch new instances to replace the failed ones. But with auto recovery, you can actually set actions on the failure of these alarms. So for example, if the instance status check fails, you can set it to automatically reboot. So if your file system gets corrupted or something goes wrong with your NIC where your virtual NIC on your instance where you can't actually reach the instance, that instance will then fail that health check and you automatically be rebooted. And same with the system level check. So if something goes wrong with the underlying hardware on the physical host, you can set an action to recover. So that instance will be automatically migrated to a new set of hardware, and it will retain all of the characteristics of that instance, all the way down to how the volumes are attached, what IP addresses were assigned to it, even the instance ID. And I note there at the bottom, this is limited to newer generation instance types which use EBS-only storage. So obviously this recovery depends on EBS to actually work. So let's get into the actual volume types themselves. So all of EBS's volume types are built on two different hardware platforms, either an SSD-based platform or spinning hard disk drive. So, and they obviously have very different characteristics. You know, SSDs are very low latency. They're very good for random I/O workloads because, you know, all points on the disk are equally reachable, versus with a hard drive, you're up to the mercy of, you know, rotational physics, where you have to get the head exactly in the right place, and if it's a random workload, that head is going all over the place and adding to the latency of actually delivering your data. But that said, hard disk drives have some very interesting qualities when it comes to getting that head in the right place and delivering sequential data very fast. So under SSDs, we have the two volume types, which I previously mentioned. So first is GP2, or general purpose SSD, which is kind of the workhorse of our fleet. It's the default boot volume type for any EC2 instance that you launch. We'll get into the actual performance characteristics in a second. And then IO1, which is our provisioned IOPS, which is the one I mentioned, that you can actually dial in the specific consistency of IOPS you want delivered, and we give that to you at a guaranteed rate. And then under the hard disk platform, we have the two new volume types that were mentioned by Matt this morning. And these are the ST1, or the throughput optimized HDD, and the SC1, or the cold HDD. And these are both throughput optimized. So that now the platform is kind of evolved in these two types of volumes. We have the SSD-based, which are IOPS performance-based, where you tell us the kind of IOPS you want, and performance is delivered on an IOPS basis, or input-output per second. And then the HDD-based, the hard disk-based platforms, which are throughput-based. So we deliver performance in a megabytes per second fashion. And what about our venerable magnetic EBS volume type that's been around since 2008? We'll get to him in a minute. But first, let's talk about the GP2. So GP2, like I said, you tell us how much storage you want, and for every gigabyte of storage you provision, you get three IOPS, up to a limit of 10,000. Each volume can support up to 160 megabytes a second of actual throughput. And then, obviously, SSD-based, so the single-digit millisecond latency is very good. And the capacity is anywhere from 1 gig all the way up to 16 terabytes. But the interesting thing about GP2 is that we introduced a burst model. So, as I described before, customers didn't know exactly how many IOPS they needed to provision, but they knew that their workloads were pretty variable and could do very well with a burst model. So we came up with this burst model for GP2, which looks like this. So for every gigabyte of data you provision, you get 3 IOPS. And it's constantly accumulating in this burst bucket, to the point where with GP2, you can build it up to 5.4 million credits. And then you can spin those credits at a rate of up to 3,000 IOPS per second. So that means you can burst up to 3,000 IOPS, no matter what the size of your volume, at any point in time. And you always can go back down to your baseline, which is the 3 IOPS per gigabyte provisioned. But the concept of burst is a little misleading, because burst implies that this is not something that you depend on for a large amount of time. Well, the fact is, even at 1 gigabyte, we're going to show you the provision model first. This shows you how fast you can get up to 10,000. So the burst itself is only up to 1 terabyte. So everything over a terabyte is obviously up to 3,000 already, so you get exactly what that is. So here we're just illustrating what the baseline of IOPS is as you provision versus the burst. And then the point at a little over 3 terabytes where you reach the maximum amount of IOPS for a GP2 volume. This is what I wanted. So burst itself. So even at 1 gigabyte, you can see you still get about 30 minutes of burst. So it's quite a significant amount of time of burst. And as you move up the scale of the amount of storage you've allocated to your volume, at 300 gig, you get 43 minutes. And that's 43 minutes of 3,000 IOPS solid. And as you work your way up the curve, you can see, at half a terabyte, you get a full hour of burst. So burst is a little bit of a misleading term. And obviously, the closer you get to 1 terabyte, the closer you get to infinity because you're reaching that limit. So what about provision IOPS? So this is our IO1 volume. You can see the performance characteristics are basically doubled as what we saw in GP2. So instead of 10,000 as your max per volume, you have 20,000 IOPS per volume. Your throughput, again, is also doubled. Instead of 160, it's 320. And the capacity is the same, maximum size of 16 terabytes. But, IO1 is designed for workloads that are steady state IOPS. They don't need a burst model. You need a guaranteed amount of IOPS for your workload. You know what it takes. It runs that day in, day out. So these are workloads like mission critical databases, transactional databases that have very consistent levels of IOPS that need to be delivered with a guarantee. So unlike GP2, you can scale up very fast to the maximum amount of IOPS for an IO1 volume. You get at 667 gigabytes, you can already provision 20,000 IOPS to a single volume. Now, what about our new ST1 volumes that are throughput provisioned? And now we move into a model where we're not provisioning the volumes themselves on IOPS, we're provisioning them based on megabytes per second. But the interesting thing about these is that we've also taken the burst model to the new magnetic-based hard drive, new magnetic-based volume. So now we have a baseline that's determined, again, the bigger the volume, the more performance. So on a per terabyte basis, you get 40 megabytes of throughput, up to a maximum of 500, which is obviously very significant over and above what we were seeing with the IO1 and the GP2 max throughput per volume. And again, we have a burst model where you can burst up to, for every terabyte you provision, you can burst 250 megabytes up to a maximum of 500. And the capacity is also interesting. So the minimum volume size is 500 gigs. So these are not volume types that you're going to be attaching for boot volumes. These will be data-only volumes. So they're obviously ideal and designed for workloads that have sustained sequential workloads. So this is anything from log processing like Splunk, data warehousing like Vertica, streaming data workloads like Kafka. So a wide variety of workload types that have sequential throughput requirements. And the burst bucket works a little bit different than GP2. So now you're accumulating based on the throughput provision, so 40 megabytes per second per terabyte. But you can build up to the size of the volume itself. So it's important to note that all these burst buckets start 100% full when you launch the volume. So the idea is that the burst bucket size for these volumes is equivalent to what it would take to scan the entire volume at full burst rate, right? So that's why you can build up to the actual size of your volume itself. And then you can spend at the actual burst rate. So let's do an example of an 8 terabyte volume. So at 8 times 40 megabytes per terabyte, you're constantly accumulating credits at a 320 megabytes a second rate. And you can build that bucket up to 8, which is the size of your volume itself, and be able to burst an entire scan of your volume at 500 megabytes a second. So here we look at those volume sizes, and as the volume sizes increase, we can see what that does both for the base values and for the burst values. And for the example we just got, you can just see there what an 8 terabyte volume looks like. It crosses the line just above 300 megabytes a second, and its burst rate is already at the max at 500. Now what about SC1? So SC1, the cold HDD, is the same platform as ST1. So it's the same basic platform. It's just you trade a little bit of throughput for a really interesting price performance curve. So we'll look at prices in a second. But the SC1 is for workloads that are also sequential based, where you need high throughput, where your workload itself is judged on the throughput of, and it lowers it from 40 to 12. So you get 12 megabytes per terabyte up to a maximum of 192. And the burst is also a little bit lower. So you get 80 megabytes per terabyte up to a maximum of 250. So this is ideal for still sequential workloads, but maybe not as hot workloads. So workloads that you're not going to be accessing as often. For example, not doing those full volume scans, multiple times a day. You might do them once a day. So these might be workloads like logging or backup or archiving of data. And so again, you look at the burst bucket model. You're always accumulating at 12 megabytes per terabyte. The bucket size, again, is related to the size of the volume. So the bigger the volume, the bigger the bucket. And you can spend it up to 80 megabytes per terabyte. And a quick look at the burst and the base for the SC1 too. So you can see it go up to 250 quite quick at about a 4 terabyte size. And then the base. So the max 16T, you're getting 192 megabytes a second. And then you have your burst up to 250. So here we have a look at all four of the volume types now, the I/O provisioned and the throughput provisioned. And the prices. So GP2 is priced per gigabyte, that's it. You set how much storage you want, and it's 10 cents a gig. IO1 is where you dial in your performance. You dial in the exact number of provisioned IOPS, and we charge you for that. And then there's also the charge for the gigabytes themselves for the storage. Throughput provision model, so the ST1 is also priced just like the GP2. You tell us exactly how much gigabytes you want, and you only pay for that. So you don't pay for any I/O for the new volumes. You just pay for the storage provisioned. And then this is a really interesting one. So, 2.5 cents a gig for the SC1s. That's cheaper than S3. So that opens up some very interesting workload examples of being able to keep data on persistent volumes that can be immediately accessed with very significant throughput to instances. Instead of maybe shuffling data back and forth from S3, you've got data sets that are sitting there ready to go. And I told you we'd cover magnetics, so let's get it over with. So magnetics been around since 2008. Its performance characteristics are, the use cases are starting to get smaller and smaller. Now that we have the new ST1 and SC1 that are ideally made for hard disk drive based workloads, the magnetic is kind of falling behind. So everything about the magnetic is best effort. So whether it's IOPS or burst, it's all best effort. There's no consistency guarantees. If you don't care about how fast your volumes boot, because SSDs obviously boot a lot faster, or if you need something that's that's small and cheap, maybe magnetic. But in general, we've sent magnetic to the AWS retirement home that we call, with his friends, SimpleDB and things like the M1 Small and the M2, and now magnetic. So this is a place that we call AWS previous generation, and that's kind of where magnetic lives now. So let's talk a little bit about some EBS best practices. And let's start with performance. And the first thing I want is to give you an understanding of how EBS actually is counting the IOPS. We've talked a lot about your burst bucket and your metrics and how they relate to the IOPS you're sending towards EBS and how much you're spending. But how does EBS actually count these things? So let's walk through a few examples, and you can see how you might be able to optimize your workload to best take advantage of how the burst buckets work. So here we have an example where an application is sending down random IOs. So these are 4 16K random IOs. There's no way for the operating system to merge these into one. It's got to send these down as unique requests for these blocks. So those get sent down to representing each train is a block towards EBS. And it has a certain capacity, but in this case, since it's a random workload, it's got to fill each car with only one block. The car can take a lot of blocks. In fact, for GP2 and IO1, it can fill up to 256K of data in one of those cars. But since this is a random workload, it's only the one. So you're going to get charged for 4 IOPS in that case. Now, what if the application actually sent down, same 16K size blocks, but they were actually sequential. They were able to be merged. So EBS sees that, sees sequential blocks coming in, and it's going to put those all up on the same car and count those as one unit. So you have a 64K unit, and you'll get charged 1 IOP instead of 4. Now, what about ST1 and SC1? They don't deal in IOPS. They deal in throughput. So in this case, we're sending down 4 1 meg sequential IOs. And ST1 and SC1, they count things in 1 megabyte units. So in this case, we can fill out an entire car, 4 cars, and have 4 megabytes of throughput counted against us. So we charge 4 megabytes a second on your burst bucket. However, and this is where things get interesting with the new volume types, if you mix and match workloads, so if you're sending both sequentials and randoms at the same time, maybe mismatch application, or the application has some components that is sending some random I/O down there, the car that with the sequential is going to get filled, but so is the random, so they're going to take up a full car just like before. And the problem with that is, obviously, you're going to get charged the same. So you're still going to get charged for the throughput, but the amount of data you actually transferred is obviously a lot less. So if you think back to our curves, if you had a workload that's driving against an ST1 or an SC1 volume, that's driving random and sequential workloads, the burst bucket is going to decline at the same rate as it would if you were sending all sequential I/O. The difference is going to be the amount of data you actually transferred with those credits. So now that we kind of have a little understanding of how EBS actually counts the I/O, let's move up one more layer and talk about the actual network between your instances and EBS, because bandwidth really matters when you're dealing with performance in EBS. So if you fire up a C3 2 extra large and launch your favorite network performance testing tool, say iPerf, and start testing away at the bandwidth, you'll find that the pipe on a C3 2x large is about 125 megabytes a second. So that means you've got 125 megabytes a second to work with as far as pushing data to and from your EBS volume. The problem is that bandwidth is shared. It's not just EBS you're accessing. You're accessing other EC2 instances. You might be accessing S3. Now, this is a shared network bandwidth allocation for all of the things that this instance might be talking to. If you fire up a C3 8 extra large, that's obviously a 10 gigabit per second instance type. You've got the full pipe for that instance of 10 gigabits, and you get a lot more bandwidth, but it's still to all of those things that you're sharing that bandwidth across. And that's where EBS Optimize comes into play. So EBS Optimize is an option to give dedicated network bandwidth to your instance that goes directly to EBS. So it's enabled by default in many of the new EBS-only instance types. So those are things like the C4, the D2, the M4. Those instances only use EBS. So they are EBS optimized by default, and that's obviously free. And if this is something that's not turned on, it's something you can turn on. It's very easy to just flip the switch and turn it on. You just need to stop and start your instance, and then you'll have the extra bandwidth. But as I showed you the C3 8 extra large before, it's not an option on the C3 8s, R3 8s, and I2 8s because they have the full 10 of the physical host underlying them. So it's up to you how you want to use that full 10. And there's a link there for the chart that shows every instance type and the actual bandwidth allocation that you will get for that instance type if you enable EC2 optimized. So on a C3 2 extra large, if we turn on EBS optimized, we get another dedicated pipe of 1 gigabit per second. So now we basically just doubled our bandwidth. So we've got 125 megabytes for everything else except EBS, and now we have a dedicated gig pipe for EBS itself. But what if we launch a volume that's a 2 terabyte GP2 volume? That's 6,000 IOPS with a max volume throughput of 160 megabytes a second. If we attach that to a C3X large, the EBS optimized bandwidth for a C3X large is only 62.5 megabytes a second and a max of 4,016K IOPS. So you can see there a huge disparity between what the volume can actually take and what your instance can actually push across the bandwidth that it has. So it's not a good fit. So if we scale up one jump, we jump up to a C3 2 extra large. Now we're up to 125 megabytes a second. It's a much better fit for that volume size. So if we need to be able to push the full throughput to that volume, now we have the bandwidth to be able to do that. So let's take a big one. So an M4 10 extra large, which has a full 10 gig dedicated network bandwidth. And when you enable EBS Optimize, you get a second pipe of 4 gig. So you got quite a lot of bandwidth to deal with. And so with this 4 gig, so about 500 megabytes a second of bandwidth to EBS, we can attach a single 8 terabyte ST1 volume, which, as we've talked about, can burst up to 500 and has a 320 base. So now you've got a good fit for that. If you wanted to burst the full throughput, you have the dedicated bandwidth to be able to do that. But what about I/O? So if we went somewhere around a terabyte of provisioned IOPS volume and dialed in 16,000 IOPS, we could certainly push a full 16,000 to that, but we still got some room to go. So if we wanted to go over and above that, even if we maxed that volume out at 20,000 IOPS, we'd still have some good overhead with 32,000 available to us over that link. So that's where striping comes into play. So here we take 2 volumes and we RAID 0 them together, stripe them together, get consolidated throughput across both volumes, their combined throughput. And so now we can actually push 32,000 IOPS. So when does it make sense to RAID? And this is really a performance decision of when to RAID. Or if your storage requirements actually do exceed on a per instance basis 16 terabytes. So if one single volume is not enough, you attach another one to be able to go beyond 16T for a single instance. Same with throughput. If your throughput requirements are greater than 500, you have one of these 10 gig, or you have this M4 10X large that can do more than 500 megabytes a second, then you would have to stripe them. And same with IOPS, if your boundaries were beyond the performance characteristics of a single volume. But what we don't talk about is using RAID for redundancy. In the old world of physical hard drives, we did a lot of RAID 5, we did a lot of RAID 6, we did a lot of RAID 10. And it's just not necessary in an EBS world. If you take this simple example of striping 2 volumes together in a RAID 0 configuration. So if you send blocks to this stripe, they're going down and they're being written to the volumes in a stripe, but keep in mind that those replicas are still there. So in essence, you're actually doing what a RAID 10 does, because you've got the same number of copies of your data, but you're not having to provision double storage, and you're also not having to waste half of your bandwidth sending down the duplication of your data. So a RAID 1, it halves the available EBS bandwidth effectively because you're sending everything twice. And same with RAID 5.6. You lose about 20 or 30% of your usable I/O because that I/O is being taken up by all those parity sends you're sending down to EBS. Now, what about volume initialization? This is something that we used to talk about quite a bit in the past. When you launch a new volume, how do you get it if you want to be able to 100% use that volume right off the bat as fast as possible, what do you need to do to get that volume ready? And there was some things you had to do in the past to be able to make that volume ready, and it's no longer the case. So any new EBS volume that you launch requires no work to get it to 100% performance. So you don't have to touch the blocks, you don't have to do any read-through of the blocks. New volumes, you just attach them and go. That's not quite the same if you create a new volume based off a snapshot. Obviously, that snapshot data itself is in S3. So that lazy load process I described before, that has to happen to get your data on the volume. So the lazy load process does start and starts streaming your data. That volume is immediately usable, but it's not going to be 100% performant until all that data is loaded. So we do suggest that you do initialize, if you want to be able to use this volume at 100% performance right off the bat, that you do some kind of initialization across it. So the best way to do that is just to do a random small block read across the entire volume space. That'll queue up all the volume, all the blocks on that volume, and they'll start coming down at an increased speed than they would just with the lazy load. And then as soon as that is complete, you'll know that all the data is loaded. So let's move on to management. So taking snapshots themselves, there's a few best practices we have around making sure all of the various places in your applications, in your operating systems, in your OS kernels, where data can be cached. So you want to make sure that you flushed all of this stuff out to disk before you actually take a snapshot if you want to ensure that you're actually getting that entire point in time state of all of the changes you've made to your data. So we recommend things like with databases, flushing database caches. On your file systems, make sure you're doing a sync or an FS freeze depending upon the file system that you use. And then once all that's done, issue the snapshot. And again, when you issue the snapshot, as soon as you get that successful return from the create snapshot API call, you're ready to go. You don't have to sit around and wait for the actual snapshot itself to complete. You know, it'll go into a pending state as it's actually transferring data to S3, but you do not have to wait for that to complete before it's available to use. What about managing snapshots? I mean, if you've got, let's say, thousands of volumes and you're taking snapshots of all of these things, this can become very cumbersome about maintaining, you know, what's on the snapshot, how long you keep it around. And so I'll give a quick example of some of the tools that you can use to actually manage all of these snapshots and be able to implement some kind of overhead and governance around all of these. And we're going to build a simple framework based around a few AWS services, including Lambda, the Amazon EC2 run command. If you're not familiar with this, this is a relatively new service that allows you to be able to automate and run commands across your entire fleet at once. So it's not the same as like an interactive SSH shell across all your instances. It's much more controlled than that. So it gets wrapped within IAM, so Identity and Access Management, controls who can issue commands, what those commands can get access to, and what they can actually run resource-wise. And it also is integrated with CloudTrail, so you get to audit exactly what the run commands do. But it allows you to do things like send a bash shell script to all of your Linux instances all at once and have them run it. Or same with Windows, send a PowerShell script to run across all your instances and do maintenance. Or in this case, we're actually going to use it to facilitate the snapshots. And there's some more information there if you haven't heard of it. And finally, robust use of tagging. So tagging is critical for maintaining, what these volumes are, what these instances are, what volumes belong to what instances, and expiration dates, as we'll see how we use tagging to drive all of this logic. It's all driven by tagging. So on our EC2 instances, we're gonna apply a couple of tags. We're gonna apply first a tag that says, this instance is actually worth backing up. Please back this up. And a second tag that actually designates any backups from this instance, what its retention date should be. So very basic tags. And then we're going to use Lambda, which can execute code serverlessly in the cloud for scheduled events. So Lambda has this ability to not only be executed on triggers, so it also can be scheduled to execute code on a set schedule. So we're going to do a daily snapshot. And our Lambda function is going to execute and search across all of our instances for any that are tagged backup. It's then going to actually kick off those EC2 run commands through API calls to EC2 run. So EC2 run is going to go through our snapshot best practices. It's going to quiesce file systems. It's going to wait for the feedback, and then it's going to issue all the snapshots themselves against the instances. And then once all those snapshots start coming in, we're going to do, the Lambda function is going to do proper tagging of these volumes themselves. And it's going to compute the actual expiration date according to the tag that's on the instances. So 30 days, it's going to compute, all right, what day is this that I'm actually issuing this snapshot, and slap that label on the snapshot itself. You are going to expire on this date. So the snapshots now have this tag that say expire me on this date that we've computed. So we're going to have a second Lambda function, again, a centralized Lambda function that every day is going to cycle through our inventory, search for any snapshots that are tagged to expire on a certain day, that day that it's run, and any of those that are tagged for that day for expiration, we'll delete them. So we've got two Lambda functions, one to actually take the snapshots and slap labels on them, and two to actually search for things that should be expired. So that's pretty much it, just two Lambda functions that can control both taking the snapshots across your fleet and expiring them, and just using a few of the AWS tools and frameworks to be able to facilitate that. So now a few words on security. EBS encryption is something we launched last year, and it applies to any current generation instance that supports the AES-NI Intel hardware. So that's the encryption hardware built in the underlying physical host that accelerates encryption. That also means that there's no performance impact to actual encryption, enabling encryption. And it's supported by all of our EBS volume types. Anything that's any snapshot that's made from the actual volumes that are encrypted is also encrypted, and any volumes you create from those snapshots are also encrypted. The data at rest is encrypted. The communication between the instance and the EBS system is encrypted, and obviously all the data on the volume itself is encrypted. And finally, there is no extra upcharge for encryption enablement. And the best part is it's just checkbox. So when you launch a volume, there's a simple checkbox to encrypt this volume, and that's pretty much it. There's only one thing I'd like to point out as a best practice, and that's where you choose the actual master key. So the master key is something that our key management system, or KMS, controls. And if you do not have a key created yet in advance, it's going to automatically create one just for EBS. And that's what you see here is the default. So as a best practice, we recommend in advance you create your own master key that you're going to use for EBS. And I'll tell you a few reasons why. So this is actually how you create a master key, a unique master key, a customer master key. You go into the encryption key setting, which is in the IAM console. So all the KMS functions are actually integrated into the IAM management console. You create a new AWS KMS master key, and you're just going to name it whatever you want it. In this case, I've named it EBS master because that's what I'm going to use it for. And why would I do this? Because if I use the default, I can't do any of these things. I can't define a key rotation policy. I can't enable AWS Cloud Trail auditing of that key and how it's used. I can't control who can use the key, and I can't control who can administer the key. But if I create my own key, and then when I encrypt my EBS volumes, designate that key, I can do all of these things. So it's always recommended as a best practice to use your own key and don't go with the default. So you can see here, we're back at the checkbox, encrypt this volume, and I've changed it to this new key that I've created instead of taking the default. And how does this actually work? So this master key, which stays always within the key management system, uses an encryption process called envelope encryption to actually do the volume encryption. So there's a unique data key that is created for every single EBS volume. So each EBS volume has its own data key. And EBS calls for the master key to encrypt that key. And so that encrypted key, which is now double encrypted, is stored as metadata with the volume itself. So whenever that volume is actually attached to an instance, and that instance needs to decrypt the data on the volume, it calls KMS to decrypt the data key, only the data key, and that data key is kept in memory to actually do the bulk encryption and decryption of the data on the volume. And that's for every volume, gets its own data key. Now this seems rather complicated for what we're doing, but there's some very unique qualities of envelope encryption that make it very suitable for this kind of bulk data encryption. And here are a few of them. So obviously it limits your exposure. If for whatever reason one of those data keys is compromised, all that's compromised is that single volume and not all your volumes. It's unique to that data volume. It increases the performance significantly because you're not shipping data back and forth between KMS, massive amounts of this EBS volume data to be encrypted and decrypted. The encryption and the decryption is happening at the place that the data is actually being created, and it increases performance significantly. And obviously it simplifies key management because you can have thousands upon thousands upon thousands of EBS volumes, but one master key can control them. And you can also have a lot of flexibility in how you use those master keys. So you could have a master key per application or per business. It's up to you how you use the master keys. But they themselves can be controlling any number of actual data keys per volume. And finally, something we launched just this year is the ability to also encrypt your boot volume. So it's a little bit different than the actual check volume process. You need to create an AMI from that. So you actually create an encrypted AMI by copying an existing AMI. So say, for example, you wanted to create a copy of the Amazon Linux AMI. You launch copy AMI, and on that you would encrypt that AMI. And then once you have that encrypted AMI copy, you can now use that to launch any number of other instances off that encrypted AMI. So that's about it. So we've talked about all the volume types, about how you can select the instance types themselves to fit your workload, how to take snapshots, how to tag snapshots, how to manage snapshots, and finally a little bit about encryption, when and how to use it. So I really appreciate your time. Thank you for being here. Please leave feedback. That's the only way we know what to add, what to do better next time. And I appreciate your time. Thank you.